So this kind of moves us to chapter 4 and alkanes. So name those molecules. Can you draw a resonance structure of those molecules? How come? That was a really quick shake of the head.
Sigma bonds.
All sigma bonds. All you have are sigma bonds. There are no lone pairs, there's no pi bonds, there's no charges, no resonance structure. Anybody got a name for the one on the left?
N-heptane.
N-heptane. One, two, three, four, five, six, seven. Your book has some prefixes. I usually ask you guys to memorize up through 12. 10's fine, probably like. I used to almost not teach nomenclature at all. And then a whole bunch of people went from my class and took the MCAT and got pissed off with me. Because like nobody asked about antibinding orbitals on the MCAT, but they do ask a lot of nomenclature. So nomenclature's relative, I mean, you need to, nomenclature is important so we can talk about molecules. It's a lot more important, I think, that you guys understand and know the names of functional groups. So I can point at a molecule and I can say that aldehyde or that ester. The name of simple molecules, the IUPAC rules to name things are just, they're lists. They're tedious. They're really important. Okay, for molecules, we want to have a unique name for every different structure. So I don't want to have a name of a compound apply to two different structures. I don't want a structure as much as possible to have two different names. Okay, so N-heptane, the N just means it's an alkane and it's just like they're all attached in a chain. Hept means there's 7. Ane means it's an alkane. So there are no pi bonds, there are no other functional groups. So for example, this would be that would be 1 heptene. 7 carbons, and there's an alkene. A carbon-carbon double bond is called an alkene. So instead of heptane, it's heptene. And the double bond starts with carbon 1. And you might say to me, look, that's not carbon 1, it's on the right. There is no right and left in a molecule. There's no up or down. It's almost like space, it's just in a flask. Okay, so you always want to minimize the number. So if the alkene is here, this could either be 1 heptene or it could be 6 heptene. So it's 1. Anybody got a name for that one? 4-methyl nonane. 2, 3, 4, 5, 6, 7. That's only 7 carbons. So yeah, you're in. Okay. So I'm trying to trick you. A lot of professors will tell you they never ask trick questions. They're lying. I will try not to do that on exams. I love it in class, trip people up. So he caught the trick though. And this is, look, again, you will do this at some point. Hopefully you don't do it on an exam. Hopefully you do it on Wiley Plus. It's Friday, it's about 9:45. You want to get out, but you want to, Dr. Jones said do a little every day. So you're quickly going through there and you're just like, 1, 2, 3, 4, 5, 6, 7, heptane. There's a propyl group. 3 carbons will be a propyl group. So you might call it 2 propyl heptane. And the trick would be that you didn't go for the longest chain. So the longest chain here is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There is no rule that the longest chain has to go left to right, has to be all in the same plane. It can zigzag all over the place. So very good. There's a CH3 sticking off carbon 4. So that's 4-methyl heptane. Did it myself. All right, 9 carbons is going to be nonane. Very good. So, go into chapter 4, look at the nomenclature rules. You're generally, for alkanes, you're looking at the longest carbon chain is the parent, the base, and then you're going to number substituents, other things that come off of that, so that you get the lowest numbers, right? This could also be 1, 2, 3, 4, 5, 6 methyl nonane. It's not, it's 4, right? You always give the first substituent the lowest number it can possibly have. So, draw a constitutional isomer of 4-methyl nonane. If you haven't read ahead or seen the PowerPoints, or if constitutional isomers confuse you, you can sit there and do them. Did I turn the camera back on?
Yeah.
Yes.
That's good. I'd hate for those folks to miss all that.
So for the methyl nonane, so it's 4-methyl nonane, but it could be like 6-methyl nonane or
That-
something else?
No, it literally couldn't be 6-methyl nonane, because then that would mean it's going to be 4 or 6,
Okay.
based on the lowest number. But it could be a different number.
It could be different.
You could move the methyl. It's just if I move the methyl to here, really what I've done is just to turn the molecule around. Right? That would still be, if I put the methyl there, then the numbers of the nonane chain would just go the other way. So this is, and actually while you're at it, while you're doing constitutional isomers, what's the molecular formula of 4-methyl nonane? Give you a hint. I gave you a wrong hint. Feel free to laugh at it. You make more stupid mistakes actually the older you get. How many hydrogens in 4-methyl nonane?
22.
It is 22. You can count them all. Personally, counting to 22 is pretty hard to do, tedious. The general formula for what's called a saturated alkane is going to be CnH2n plus 2. And the way to think about that, I've written C7H16 over here, right? If you think about that, how many hydrogens are on the carbon I'm pointing at? 2. There? 2. There's 2 on all those. At the ends, how many are that? There's 1 more, right? So you got a CH2, and then you got to cap it off. That carbon's going to need 4 bonds. So basically, every carbon, if it's a straight, like if it's an unbranched straight alkane, every carbon's going to have 2 hydrogens, and it's going to be bonded to 2 carbons, except for the end carbons, which are going to need 1 more hydrogen to sort of cap off the chain. Okay, so 7 carbons, 7 times CH2 is 14, plus the 2 on the ends, CN, so 14 plus 2, 16. So 4-methyl nonane is going to be C10H22. Constitutional isomer. The easiest thing to do for a constitutional isomer is to move the substituent one thing. Right? So if we do that, I lost focus. This would be 3-methyl nonane. I hope I drew that right. I'll check it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Yeah, that's 3-methyl nonane, so that's going to be a constitutional isomer. Constitutional isomers are molecules that have the same molecular formula but different connectivity. Okay, so they can't be resonance structures of each other because they're connected differently. Some constitutional isomers can have really similar properties. 3-methyl nonane, 4-methyl nonane would be really hard to separate from each other. They're basically the same size, they have the same surface area, they have the same polarity. They're going to have really equal solubility. It's going to be a pain to get those away from each other. That's why I said gasoline the other day is this collection of octanes. A whole bunch of different constitutional isomers of octane, basically. There's some other stuff in it. It's hard to separate them. The way we make gasoline, we take crude petroleum, we distill it, we fraction by boiling point. All right, so at some point in this 20-story tall distillation column, there's the gasoline door, so you open it up, the gasoline pours out. That's all the molecules that sort of boil at that temperature. So all these constitutional isomers that are really similar come out. They all burn in your engine. You get power. There's no reason it would cost a fortune, right? It would probably raise the price of gas an order of magnitude to have like pure N-octane versus 2-methyl heptane. And it wouldn't do you any good. So, some constitutional isomers will be really different. Ethanol and dimethyl ether have exactly the same molecular formula. One is not soluble in water, is a gas at room temperature, is an anesthetic. One is soluble in water and can make you feel pleasant on a cool winter night. That is not advocacy. That is just fact. Can also make you feel really bad on a cold winter morning the next day. Okay? So, very different compounds. Again, you can sort of count them all, but I'm going to show you a real easy trick. Counting the hydrogens can be pretty hard. If you look at heptane and heptene, they're not constitutional isomers. They have different molecular formulas. They're not isomerically related at all. And the reason is there's a double bond. I'm putting in parentheses or a ring because the ring is not always it's not always called an unsaturation. Chemically, a ring is very different than a pi bond. The chemistry of alkenes we're going to look at this semester. Alkenes often do similar chemistry, and that chemistry is really not similar to what the rings are doing. But for purposes of counting hydrogens, an unsaturation is one pi bond or one ring. Right? So think about going from heptane to heptene. Let's number these. 1, 2, 3, 4, 5, 6. For N-heptane, you can number left or right, doesn't matter. So in heptene, the purple molecule on the top, how many hydrogens are on carbon 1? 2, right. I forgot which one I asked for. Right. Carbon 1 has 2 bonds shown, that means there's 2 hydrogens not shown. In heptane, how many hydrogens are on carbon 1? 3. Right? The end of the line is a methyl. So you have to take a hydrogen off carbon 1 to open up a spot to make that double bond, to make a pi bond. That's not chemically how the reaction works, but thinking about it, that's what has to happen. Carbon 2 in heptene, how many hydrogens? 1. Carbon 2 in heptane, 2. So to make this double bond, we have to take a hydrogen out of C2 and a hydrogen out of C1. That's 2 hydrogens go away. And so if there's one unsaturation, call this a unit of unsaturation. The molecular formula is going to be CnH2n. Right, because that 2n plus 2 that we had in the saturated alkane, right, that 2 goes away. All right, so a unit of unsaturation, again, is a ring or a pi bond. Every ring and pi bond this molecule is called cycloheptane. 7 carbons in a ring, so cyclo. What's the molecular formula of cycloheptane? Right. So let's number these. How many hydrogens are in each carbon? 2. They're all CH2s. Basically, we've taken, in heptane, we've taken the hydrogen off 7 and a hydrogen off 1. We've bonded them. Again, that is not how the chemical reaction happens. But that's, thought experiment-wise, that's what happens. So, does cycloheptane have a constitutional isomer anywhere on the board? Yeah, so 1-heptene, cycloheptane are constitutional isomers. Same molecular formula, they're connected differently. Right? The difference can be small, the difference can be large. So 4-methylnonane, 3-methylnonane are constitutional isomers. There's a really small change. Methyl moves, the methyl's on adjacent carbons. Cycloheptane and 1-heptene, pretty big change. Right? 1 and 7 are bonded in one, they're not bonded in the other one. There's a pi bond in one, there's not a pi bond in the other one. The chemistry, again, you could separate 1-heptene and cycloheptane pretty easily once you learn how to separate stuff. All right? You could draw then another, we could just shrink this ring. That's a really lazy, I'm out of practice, sorry. I don't know why I'm out of practice, I've been drawing these all free. So a 6-membered ring, there are 6 carbons in that ring. This is going to be a cyclohexane. A methyl sticking off. So this will be methyl cyclohexane. Can't spell. And now here's the trick. Instead of counting hydrogens, count the heavy atoms, carbon and the heteroatoms. Cycloheptane, methyl cyclohexane, each have 7 carbons. Do they have the same number of hydrogens? Okay, counting to 14 is maybe not the worst thing you've ever done. Let's say you had 87 carbons. Now counting every hydrogen is going to be a pain. What you can do is count up the units of unsaturation. So if 2 molecules of exactly the same number of heavy atoms, in this case carbon, right? They each have 7 carbons, and they each have 1 unit of unsaturation. Therefore, they're constitutional isomers. Right? So 1 ring in cycloheptane, 1 ring in methyl cyclohexane. Make sense? That took way longer than I thought. Here's the last thing I'm going to tell you. Maybe. Maybe I'm just going to tell you. All right, this is a program called ChemDraw. If you go to the intro module of, our Canvas page, you can find, there's just a thing called ChemDraw. You can download this to your computer. You can draw molecules. You'll have to play around with it some. It works a lot like the Wiley Plus graphical interface to draw molecules. It's not exact, it's pretty close. You can do some cool stuff here. You can see there it's got an analysis window to give you the molecular formula. If you want to practice, you can draw a whole bunch of different molecules and try to figure out which, work with a friend. You draw 5 molecules, make sure there's some constitutional isomers in there. You can ask them and then you can check it with this. And then the other program you can use, let me copy that. I was going to go through this in a bit more detail. I'll do that on Tuesday, so make sure you look at the video. This program is called Chem3D. Maybe a lot of you have bought model kits. I don't know if you have or not. I like those. You don't have to have a computer. You don't have to worry about software working, and it's something physical you can turn around. But you can draw or paste in ChemDraw figures. Come on, put it in there. Good, this is nice. Don't do this in front of your class. There. Right? So then you can get an electronic 3D model. You can play with this. We can look at it. We can look at it from all sides. Again, these structures, the next thing we're going to do in chapter 4 is kind of look at conformational analysis. Sigma bonds, if you think about it, they're just cylindrical. So you can spin freely about them. It's like a handshake if we're in space. If we're in the space station, right, on Earth, we basically have to both be standing up, right? But if we're in the space station, you could be this way, you could be up. It doesn't matter. The pi bond, though, because it's got 2 points of contact, right? If I wanted to high-five you and kick you in the ankle at the same time, like there's not different ways to arrange that. There is one way we have to be oriented. So around sigma bonds, there's free rotation. The molecule can rotate however it wants. For a pi bond, that holds everything rigid. All right, that's it. I've gone over. I apologize. There's a quiz. Quiz 1 for formal charge uploaded yesterday. It's due Saturday. Quiz 2 for molecular formula went live 2 minutes ago and is due Sunday. So make sure you've done some Wiley Plus. Make sure you've read the book, looked at the PowerPoints, and when you're ready, go ahead and work those. 30-minute time limit, one answer, you get one attempt.